Deep convolutional neural networks and their variants have led to remarkable progress in computer vision. So much so that for the task of ImageNet classification, these methods have boasted better performance than that of humans themselves. However, computers are still far from attaining human-level performance on perception for real-world scene understanding. Occlusions, clutter, and the limited resolution of the visual signal are just some of the many problems that make this an especially challenging problem to solve. Meanwhile, context has been shown to be an extremely important cue for scene understanding and has led to impressive performance gain in literature. We propose a deep network topology that incorporates 3D contextual cues for holistic scene understanding. Taking a depth map from RGBD sensor as input, we represent the scene in 3D. Instead of using a sliding window approach or region proposals that consider each object separately, we directly feed the whole 3D scene into a 3D convolutional neural network to output the locations and size of all major objects for scene understanding. To encode the context in the network, we define 3D scene templates. Each scene template corresponds to a functional area in a scene performing particular functionality in which the arrangements of major objects are similar. In this paper, we define 4 commonly used functional areas, including sleeping area, office area, lounging area, and table and chair set. For each functional area, we use the training data to learn the number of instances of each object category and their size and location. We call each such functional area with furniture in relatively fixed locations as a scene template. Like here, a typical sleeping area contains a bed, 1 or 2 nightstands, lamps, some dressers, and sometimes an ottoman. The office area typically contains a desk with some chairs and maybe some monitors and speakers on the desk. The lounging area usually comes with a coffee table surrounded by sofas and chairs, and occasionally an end table and lamp on the side of the sofas. The table and chair set is a table surrounded by chairs. This usually appears in dining rooms and conference rooms. To perform the scene understanding, we first convert the depth image to a 3D volumetric representation, and then feed it into a transformation network, which tells us a rigid transformation containing a rotation and translation that aligns the given scene with a predefined scene template. The right-hand half shows the top view of the point cloud. We can see that the initial alignment is good but not perfect due to the diversity of furniture arrangements. After aligning the given scene with a scene template, its 3D volume is fed into the 3D context network, which tells us whether or not each object in the scene template exists and how their positions and sizes should be changed towards the correct case. The final 3D scene understanding result is obtained by integrating the network output and the predefined scene template. We show some comparisons between our method and deep sliding shapes, which is the state-of-the-art standalone 3D object detector that does not use context. Compared to object detectors that focus on local appearance, our method benefits from 3D contextual cues in many cases. First of all, context can remove false alarms that result in unnatural arrangements, such as a table on top of another table, shown here in the middle, and the nightstand and table here, at the end of the bed. Secondly, context also helps find objects under heavy occlusions, such as the nightstand on the right-hand side. Context is also very helpful for finding objects with weak local evidence. For example, monitors usually look like planar surfaces with missing depth, and local features are not strong enough to detect them. However, our context model can strengthen the signal from the local features by knowing that a monitor is very likely to be located on a desk. Again, deep sliding shape recognizes the table as a nightstand due to their similar local appearances, while our context model can successfully avoid such a false positive. Here we show more results from sleeping areas, office areas, lounging areas, and table chair sets. On the top, we show the depth image overlaid with ground truth and our results overlaid on the color image. On the bottom, we show the initial scene template overlaid on both the color image and a top view of the scene's 3D point cloud. On the right, we show our results in 3D overlaid on the scene's 3D point cloud. Thank you for watching.